All right, welcome to this explainer. Today we're taking a bit of a microscopic journey. We're going to completely decode the dense, heavy math behind fluid dynamics and actually turn it into a story about the invisible forces that are literally shaping our world. We'll be looking at the hidden equations governing materials we interact with every single day, taking a really intimidating web of mathematics and translating it into clear, easy-to-grasp concepts.
Now, right off the bat, I want you to think about a pretty simple question. What do blood, liquid plastic, and crude oil all have in common? I mean, if you pour a glass of water, you generally know exactly how it's going to behave, right? It flows predictably. But these substances, they are absolute rebels. They do not follow the normal rules of flow. If you subject them to pressure, or heat, or magnets, their behavior completely transforms. And to understand why that happens, we have to look closely at the underlying physics.
So, here is a quick look at our roadmap for today. Number 1, we'll meet the Maxwell fluid. 2, explore the complex flow environment. 3, decoding the math. 4, the battle of forces. And 5, real-world engineering impact. Let's dive in.
Section 1. Meet the Maxwell fluid. And trust me, this is not your average liquid.
Think about a simple Newtonian fluid, something like water or apple juice. They follow really simple, predictable rules of flow. But then you have non-Newtonian fluids, things like blood or liquid plastic. Like I said, they're rebels. Their consistency literally changes depending on the forces you apply to them. That means a single, simple equation just cannot capture how they move. It's way more complex. And within that non-Newtonian family, we have the absolute star of our explainer today, the Maxwell fluid. Now, a Maxwell fluid is entirely unique because it has what physicists call elastic memory. It doesn't just flow, it actually remembers. It has both viscous flow properties, kind of like honey, and elastic properties, like a rubber band. This gives it a unique viscoelasticity. Basically, if you try to deform it suddenly, it's going to resist and push right back at you.
Moving on to Section 2, the complex flow environment. We are essentially setting up an obstacle course here.
Okay, so to understand this obstacle course, we have to tackle a pretty intimidating term, magnetohydrodynamics, or MHD for short. It sounds like a lot, but we can define it super simply. It is just the study of how magnetic fields push and pull on electrically conducting, moving liquids. Just imagine your fluid is carrying an electrical charge, and you suddenly introduce a massive magnet into the mix. The resulting interplay between the fluid dynamics and the electromagnetism creates some incredibly powerful new forces.
So here is the exact, frankly chaotic, obstacle course the researchers built mathematically. First up, they have an infinite vertical plate that oscillates back and forth, which generates shear movement in the fluid. Second, the fluid isn't just sitting in an open tank. It's actively being forced through a porous medium, which acts kind of like a rocky resistive sponge. Third, they apply thermal energy to create heat transfer and temperature variations. And finally, they blast the whole thing with external magnetic fields. We are literally tracking how this Maxwell fluid reacts when subjected to oscillation, sponges, heat, and magnets, all at the exact same time.
Section 3. Decoding the math. How do we make sense of all this chaos?
To actually solve this, researchers took pages and pages of intimidating partial differential equations and condensed them into a rigorous logical flow. Step 1. Set up the governing equations for momentum, energy, and shear stress. Step 2. Apply a really specific mathematical tool called the Laplace transform. And Step 3. Calculate the exact velocity and temperature profiles.
Now, that second step, that's the secret sauce. The Laplace transform is essentially a mathematical magic wand. It takes highly complex, really messy, changing fluid movements and neatly converts them into easily solvable algebraic equations. Because of this transform, the researchers weren't just guessing. They found exact, calculated solutions to this incredibly complex problem.
Which brings us to Section 4, the battle of forces. Think of this as a microscopic tug of war.
This is where we see exactly which forces speed the fluid up and which ones act as a drag. We've got the Grashof number fighting to accelerate the flow, while the magnetic and Maxwell parameters fight to suppress it. And the permeability parameter, well, that acts as a sort of mediator. Let's actually break these down a bit more so they make sense.
First, I want you to think of the Grashof number as the gas pedal. This number represents thermal buoyancy. You know how hot air rises? Well, similarly, when thermal energy is applied to our fluid near that oscillating plate, it creates buoyancy.
So an increase in Grashof number means stronger thermal buoyancy, which literally causes the fluid's velocity near the plate to drastically accelerate and surge forward.
On the flip side, the magnetic parameter acts as the brakes. When you increase the magnetic field on this electrically charged liquid, it induces what physicists call a Lorentz force. This electromagnetic force actively opposes the fluid's motion. It completely suppresses the flow, it dampens the velocity, and it physically shrinks the fluid's boundary layer. It's hitting the brakes hard.
Then we have the Prandtl number. This dictates how easily heat spreads through the fluid. For a fluid with a high Prandtl number, heat gets trapped. It gets trapped right near the plate, creating a very localized thermal layer, which lowers overall velocity. But a fluid with a low Prandtl number, that allows thermal energy to diffuse super easily and rapidly, creating a thicker thermal layer that effectively boosts the fluid's momentum.
Now, we also have to remember that the plate causing all this movement is actively vibrating. The researchers tested both cosine and sine wave oscillations. Cosine starts with this immediate, jerky impact on the fluid, while sine starts at 0 and smoothly builds up momentum. But, the really beautiful mathematical takeaway here is that regardless of how you shake the plate initially, the transient turbulence eventually dies down. Over time, both decay into completely predictable, steady-state flow patterns controlled entirely by our mathematical parameters.
Section 5. Real-world engineering impact. Why does all this math actually matter?
Well, it matters because these microscopic equations govern entirely different massive industries. In plastic extrusion and polymer processing, the material behaves exactly like our Maxwell fluid. In oil reservoir engineering, if you want to pump really thick crude oil out of porous rock deep underground, you absolutely have to know this math. It applies to modeling blood flow in advanced bioengineering, and crucially, in designing passive cooling systems for things like miniaturized nuclear reactors and high-end electronics, where heat and magnetic fields are constantly interacting.
As the researchers noted in their findings, and I'll just quote this directly, the analytical solutions provide valuable insight into the transient and steady responses of Maxwell fluids, offering a useful theoretical foundation for engineering systems involving viscoelastic and MHD flow phenomena. So, this isn't just some abstract math exercise. It is literally the blueprint for building the next generation of fluid technologies.
Which leaves us with a final, pretty massive question to consider. As we continue to push the boundaries of engineering, building hotter microreactors, extracting resources from even deeper porous rock, and designing microscopic biodevices for the human body, how will mastering these unseen fluid battles shape our technological future? The invisible equations we explored today are quite literally designing the physical world of tomorrow. Thank you so much for joining me on this explainer, and remember to keep questioning the unseen forces all around you.